Alright, in this video I want to do a couple of examples for the applications of systems of linear equations. Alright, so our first example will be this one. Alright, ticket prices at a local movie theater are $10 for adults and $7 for children. At one performance of a new children's movie, 335 people attended. If the total revenue for the performance was $2,741, how many adult tickets and how many children tickets were sold? Alright, so begin like we always do with word problems and define our variables. So let X be the number of adult tickets that are sold, and since we're looking for two things, we'll let Y be the number of children tickets sold. Alright? So, as usual with most word problems, the hardest part is coming up with the equation, right? Or in this case, there's going to be more than one equation. So we're looking for two things. We need two equations. So how do we determine that? Well, we know that if X is the number of adult tickets sold and Y is the number of children tickets sold to this particular performance, and we know that 335 people attended that performance, then we can get an equation, right? We know that X plus Y has to equal 335, right? That's the total. X plus Y, adult tickets plus children tickets equals the total 335 tickets sold. So there's one equation. We just have one more to go. Right? So now we bring in the dollar amount. So like this first equation here is the total amount, the total number amount, and the second equation we're doing here is going to involve the money. All right? So we know if it's $10 for adults and $7 for children, then we've got 10x right there. That'd be the total amount of money brought in for the number of adults that have attended that performance, plus 7y. This is the total amount of money brought in by the number of children tickets sold for the performance. And we know the total revenue for the performance was $2,741. And that's your system of equations that we can solve using the elimination method, substitution method. All right, so I'm going to solve this with the elimination method. I'm going to multiply this top equation here by, I'm going to eliminate the x, so negative 10. So that gives me negative 10x minus 10y equals negative 3,350. I'm going to leave the bottom equation alone. So that's going to still be 10x plus 7y equals 2,741, right? And then add them up. So the x's go away, right? And this gives us negative 3y equals negative 609. Right? So then y equals 203. Right? So what does that mean? Well, that means that 203 children tickets were sold. Right? So now we need to figure out the number of adult tickets, right? We'll take the 203, plug it in for y here, right? So don't forget to find that. So x plus 203 equals 335. So x equals 132. Everybody see that? So 132 adult tickets and 203 children tickets. All right, make sense? All right, let's do one more. All right, so we have a chemist would like to make 15 liters of a 23% acid solution by mixing a 12% acid solution and a 27% acid solution. So how many liters of each solution should the chemist use? All right, so again, we set up our system by first defining our variables. Okay, so let x be the number of liters of 12% solution, and let y be the number of liters of the 27% solution. All right, so that's the number of liters of each solution we want. We know we want to make a total of 15 liters. So x plus y has to equal 15, right? Number of liters of 12%, number of liters of 27% equals total number of liters. Right? So there's the first equation. Now we've got the percentages that we need to bring in here, right? So if x is the liters of 12% solution, then of that total amount of liters, X, how do we calculate that 12% of that is acid, right? So you have the percentage, change to the decimal number, so 0.12 times X, right? And then we've got the 27, so 0.27 times Y, right? So this is going to be the total of these X liters, all right? 12% of those X liters is pure acid there, right? And of this other acid solution, 27% of the total number of liters Y is pure acid. So we want that to be equal a new solution, right? So how many liters will be in this new solution? Well, 15, right? And what's the percent acid solution we want of those 15 liters? Well, it's 23%. So we need to have 23% times 15. Right? So percentage times amount plus percentage times amount equals percentage times amount. Right? So you have that balance with the equation there. All right, there's your system. So we just need to solve that system using the substitution elimination method, and that's it. So, all right, note that 0.23 times 15 is 3.45. Okay. So I'm going to multiply this bottom equation here by 100 to get rid of all the decimals, and that'll give us 12x plus 27y equals 345. Okay, and then this top equation I'm going to multiply, because I want to eliminate the x's, right? So I'm going to multiply by negative 12. I could have chosen the y's to eliminate, and then we would multiply this top equation by negative 27, right? But I'm just choosing the x's. So we have negative 12x minus 12y equals negative 180. All right, then add them up. X's disappear. We have 15y equals 165. So y is 11, right? And if x plus y is equal to 15 and y is 11, that implies that x has to equal 4. So we need 4 liters of 12% solution and 11 liters of the 27% solution in order to make 15 liters of that's 23% acid solution. All right? All right, I want to do one more example. It took Melanie 5 hours to motor a boat 45 miles upstream. Her return trip the next day took 3 hours. Find the speed of the boat in still water and the speed of the current. Right, so that means the speed of the boat in still water means there's no current in the water. It's perfectly still. How fast is the boat going? And then when you factor in the current either speeds the boat up or it slows the boat down. So always begin by defining your variables. So let x be speed of boat in still water and let y be the speed of the current. All right, and then everybody see that we've got distance, rates, and times going on here. You know, we're looking for rates. We're looking for the speed of the boat in still water, and we're looking for the speed of the current. So those are rates. We've got distance, right, because they go 45 miles, and then we've got time, 5 hours and 3 hours, depending on which way she's going, right? So I like to set up this little chart, right, where I have distance, rate, and time going across the top here. And then we have two things going on here. She's going upstream, which is this first row, and then downstream, which is this second row. We're going to fill in these 6 boxes is the plan. Right? So for upstream, the distance that she goes upstream, it took her 5 hours to motor a boat 45 miles upstream. So the distance is 45 miles upstream. And her return trip the next day, so she's returning this to the same place that she started the next day. So the distance going downstream is 45 miles as well. So both the distances are 45 miles. All right, so now when she's going upstream, the time it took her to go the 45 miles is 5 hours. And then downstream, it took her 3 hours to go back down. All right, so now it's the rates that we're talking about. Well, if we've got if we have no current and the water is perfectly still, then x is the speed of the boat. And so the boat speed's just going whatever that is. Da, da, da. But picture a current pushing the boat, right? So say the boat's going downstream. It's going with the current. When we say it's downstream, it's going with the current, right? So the current is pushing the boat even faster than what the boat would be going if it was just in still water, right? As opposed to upstream, you've got the boat fighting against the current. So the current is actually slowing the boat down because it's pushing against the boat, right? Are you with me on that? Right, so how we compensate for that with the rate here is, well, if we're going downstream, we've got the speed of the boat, whatever that is, plus the speed of the current. That would be the total rate of the boat as it's moving downstream. Because the boat is going downstream, it's going with the current, so the current is making the boat go faster, right? Whereas if it was going upstream, the speed of the boat minus the speed of the current, because they're fighting, they're doing opposite things, right? The current is actually slowing the boat down, right? So we have x minus y would be the actual rate of the boat as it's going upstream, right? And we always want the speed of the boat minus the speed of the current, because we're hoping that the speed of the boat is actually faster than the speed of the current, because if the speed of the current is faster than the speed of the boat, then we have other problems to worry about than solving this math problem. All right, so the same idea works for say like airplanes with the wind, right? With the wind, against the wind. It would be the same type of setup. Speed of the plane against the wind, speed of the plane with the wind. So it's the same idea for those boat and airplane problems, all right? All right, so we filled in our chart. Now, what's the relationship between distance, rate, and time? Well, we know that distance is equal to rate times time. So we know that 5 times x minus y has to equal 45. Well, that's one equation. 5 times x minus y equals 45. And we also know that 3 times x plus y has to equal 45, just from our chart. And the fact that we know that distance is equal to rate times time, right? Ready to see that? Okay, so then this means that we can divide both sides by 5, right? This is 5 times x minus y equals 45, but we can just divide both sides by 5 and get x minus y is equal to 9. And down here, we can divide both sides by 3, because it's 3 times x plus y, and that would just give us x plus y, and 45 divided by 3 is 15. And this is our nice little system that we have to solve for x and y, right? And everybody see that we can just add them up right away, right? And the y's are going to go away. So we get 2x is equal to 24. So x is equal to 12. Right? And what did x represent? It represented the speed of the boat in still water. So the speed of the boat in still water is 12 miles per hour. All right? So we know that x plus y has to equal 15, right, from just this above equation right here. So that implies that y has to equal, well, if x is 12, 12 plus what equals 15, y equals 3. So the speed of the boat in still water is 12 miles per hour, and the speed of the current is 3 miles per hour. All right, so again, same idea with the speed of the airplane going with the wind or against the wind, right? Same idea. You can set up this little distance, rate, and time chart and let that help you figure out the actual equations for your system. All right, that's it. Study well. Please let me know if you have any questions.